Okay, I gave you guys each a worksheet that has some practice questions on it. It's not for marks, it's just if you want more practice on this, there's a worksheet. So let me re-go through this concept just one more time, just to see whether it helps sink in even more. Why does water have a pH of 7? We didn't arbitrarily just pick 7 as a number. 7 actually has a purpose. The purpose was that water, as odd as it is, 2 times in a billion, has the ability to break apart. I'll even try to diagram it here. Water is H and OH. And if you looked at a bunch of water molecules, they'd all be stuck together. But 2 times in a billion, they'd break into pieces. Very rare, but still happens. Does that make sense? So even pure water actually has some acid in it. And even pure water has some base in it. Exactly equal amounts. I mean, as soon as this guy falls apart, some other H's and OH's are probably going to come back together. Does that make sense? So 2 parts per billion basically means this concentration number here, 1 times 10 to the minus 7. We are then always comparing to this number, 0.000001. That's the number we're comparing to. So if we're talking about acid, if you have a higher number than that, you're acidic. Or if you have a lower number than that, you're basic. But if you have a lower number, it actually means you have more hydroxide than hydrogen. So if I have my hands like this, if one goes up, the other must go down. Does that concept make sense? So, for example, if I gave you this number right here, what is approximately the pH of that number? 2. Because there's only 2 zeros. That's basically what pH does, is it tells you how big is the number, or how little is the number, and it's based on how many zeros there are in front of the values. Does that make sense? So this is a pH of 2 point something, whereas if you had this number right here, this is well past what normal water would have. So if we were talking about acid right here, this would have a pH of 6, 7, 8, 9, 10. This would have a pH of something of 10. A pH of 10 is not actually even an acid. Technically, it's actually a base. So that's why high pH numbers are bases. If you can wrap your mind around that concept, that's fantastic. If you can't wrap your mind around that concept, but you can at least still do the math, you're fine. Okay? So really it comes down to, can you work with these formulas right here? And so if you still want more practice, that's what that worksheet's for. Sound good? Okay. My first couple slides then after this really talk about the same stuff I've just been saying here. Some students mistakenly think that acidic solutions have low pH values. But hang on. Some students have difficulty with the idea that acidic solutions have low pH values. Often kids, when I say, let's try to make it more acidic, they would say, well, that means you have to increase the pH. Let me say that again. If you want to make something more acidic, do you want to increase the pH? The answer is no. To make something more acidic, you actually want to decrease the pH. Because by decreasing the pH, you're making it so that there's fewer zeros in front of the number, thereby making the number itself actually bigger. Does that make sense? So, and then I just have a slide here kind of talking about how if one goes up, the other goes down, that kind of concept. So like if you have a pH of 1, it must mean that you have a very high concentration of H+, but it means you do have OH-. It just means you have a very low concentration of OH-. Because if they both started at 10 to the minus 7, if one goes up, the other goes down. So even in like a highly concentrated acid, you actually should be able to find a few particles of OH. Sounds weird, but water has that ability. And just one more picture talking about the idea of, here is something that is clearly acidic. Look how many hydrogens are there. But you will see an OH sitting there. These 2 guys would probably turn into water. And then another water would probably over here turn into an OH and an extra H. Does that make sense? I hope it's sinking in. Okay, here's the point of today's lesson. If we want to find the pH of a solution, there are a lot of empirical tools that we can use. I'm going to close that door. Yesterday you guys did a lab. What sort of empirical tests do we have to tell if something's an acid or not? Sure, litmus works. So you could use universal litmus paper, which is more or less yellow, and hopefully it will change a shade of blue or green or a shade of red, hopefully. You could also use red litmus paper or blue litmus paper. And then, like, say you use blue litmus paper and it stays blue. It means it's maybe a base, or it could be neutral. Does that make sense? But if you have blue litmus paper and it turned red, then we know for sure it's an acid. So litmus is not a bad indicator. What else can we use? Yeah, a magnesium ribbon often will work well. It'll bubble if it's in the presence of an acid. I think I even still have the equation written on the board there. Magnesium plus an acid should produce hydrogen gas. I know, Michael, your group in the acetic acid, you could like see it bubble quite vigorously. Did anybody else's group in the acetic acid have it bubble quite well? So you could see that.
It like stripped it and made it white.
Yeah, like what it was doing, it was stripping away the outer coating, and so I don't know that it was so much white as it was almost like it was polishing it. Often, like polishes will actually take off the outer coating, because maybe there's a bit of rust on the outer coating. So another test you could do then is you could use a pH meter, and that will just tell you what the pH is right off the bat. Well, today I want to talk to you guys about another empirical test, and it's going to be the focus of our next lab on Thursday. They're called indicators. So there are many substances that can indicate the presence of an acid or a base, and if it changes color, it's called an acid-base indicator. You guys have already worked with one of them. Litmus paper is actually a piece of paper where they put an indicator on the paper. And litmus has a really cool property in that litmus changes color between 6 and 8. If litmus happens to touch something that is a pH lower than 6, it usually turns red. And if litmus happens to touch something that is bigger than 8 for pH, it usually turns blue. But litmus is not the only indicator that we've discovered. And so what I want to talk with you guys about is how there's a table in your book that has way more indicators than just litmus. So it is on page number 10, like the last page in your data book. It looks something like this. You can find this chart. The title would be Acid-Base Indicators. So litmus is actually not listed on this particular book, is it? If litmus was in this particular book, it would be right underneath bromothiamyl blue. Can you guys find where bromothiamyl blue is? It's about 2/3 of the way down the page. If litmus was an indicator listed here, litmus, the way it works is it changes color from 6 to 8. If litmus touches something that's below 6, it would turn red. And if it touches something above 8, it would turn blue. Well, there's more indicators out there than just litmus. So let me pick another example here. Let's say we picked bromothiamyl blue. Let's say we had bromothiamyl blue paper. What color would bromothiamyl blue be if it was in an acid? Can you guys interpret how this chart would work? Okay, do you guys see how like bromothiamyl blue is, I don't know, most of the way, like just under halfway down? You see how it says between 6.0 and 7.6? Okay, and then after that it gives you colors?
Yeah.
Okay. Anything less than 6.0 would make bromothiamyl blue be yellow. Anything bigger than 7.6 would make bromothiamyl blue be blue. Does that make sense? Then one more thing. What if the pH was right at 7? Anybody have an idea what color that would be? Green. Why green?
Because yellow and blue
make green, yeah. So like basic color theory. The way indicators works, it's 3 different ranges. Okay, there's the low side, that's going to be a color. Then there's the in-between, that's going to be a different color. And then there's on the big side, that'll be a third color. And the way this chart works is it only actually lists the low color and the high color. Does that make sense? So, like for example, phenol red is right below it. If phenol red touched something that had a pH of like say 1 or 2 or 3, it would be yellow. If phenol red touched something that was clearly a base, like 8, 9, 10, 11, 12, it would be red. But if phenol red was in a neutral solution, like say 7, it would be orange. Because red and yellow make orange. Does that make sense? Okay. So that's basically the chart. My goal then is just to show you how we can use it to try to figure out pHs of solutions. So, I have a picture on here of what litmus would look like if we had an indicator of it. I actually have litmus indicator. We're going to do a lab on Thursday where I'm going to give you a solution. I'm going to tell you its pH. Well, actually, I won't tell you its pH at first. And I'm going to ask you to use a whole bunch of indicators and try to narrow down the pH range and figure out what the pH of the solution is using different drops and how they change colors. But for example, this picture here, litmus, if it's an acid, litmus is red. And if it's a base, litmus is blue. You guys had learned that before. All I want to do is add a whole bunch more indicators. You don't have to memorize them. You just have to know how the chart works. Does that make sense? I do have a side note on here. These indicators are very complex organic compounds. To be honest, I don't need you guys to know these suggested abbreviations. But in case you're wondering how these abbreviations work, indicators are technically acid-base systems on their own. For example, methyl violet. You see how it goes HMV, then it goes MV negative. The HMV is like the acid version of the indicator, whereas the MV negative would be the base version of the indicator, because one of them has a hydrogen and one of them doesn't. That is not something you need to worry about at all, not even in grade 12 to be honest. But in case you're wondering what that means, they have abbreviations, and typically there's an H in front of it, and then there's not an H in front, referring to the fact that half of it's acid and half of it's base. So let's hop to an example here. I'm just going to go right to the back page here. I'll come back to the ones I skipped. On Thursday, I'm going to give you an unknown solution, and I'm going to give you a whole bunch of indicators. And what you're going to do is you're going to take a test tube, you're going to put a little bit of the solution in, you're going to put the indicator in, and you're going to see what color it turns. So imagine these are some results you have. Let's say that orange 4 was yellow, Crescal red was yellow, and methyl orange was red. Let's try to figure out approximately what the pH is. Here's how I recommend you try this. Make a pH chart. So like, here's a pH chart. Typically pH goes from like, say 0 to 14. So, and I kind of draw it like this-ish kind of thing. We haven't covered this yet in math, but in just under a month, we're going to talk about something called reverse shading. We're going to do reverse shading here. Let me show you what it looks like. Orange 4 being yellow. Can you guys find orange 4 on here? It's the fourth one down. What sort of pHs would orange 4 have to be if it was yellow? More than 2.8. Does that make sense? Okay, using reverse shading, we're going to shade in the places where it is not. Okay. So I'm just going to put a little bar right here for 2.8, and I'm going to shade this section right here and say my pH is clearly not down here. Does that make sense? Pick another one. Crescal red is yellow. So first we got to find where Crescal red is. Crescal red is actually an odd indicator in that it is yellow in two different spots. Do you guys see how it means that it's above 1.0? But do you see how the one right below it goes from 7 to 8.8? So that means it's somewhere between 1 and 7. So what I'm going to put down is I'm going to put down 1 right here. And I'm going to shade right there, which actually doesn't add anything new to it. And then it also has to be between 1 and 7. So that means anything above 7 I'm going to shade, because that's clearly not where my range is either. Let's try one more then. Methyl orange is red. So methyl orange is the fifth one down. What sort of pHs does it have to be if methyl orange is red? Below 3.2. So I'm going to write in 3.2. It has to be below 3.2. So I'm going to shade everything that is above 3.2. Even if it means that I shade something a second time. See how I'm kind of reshading this a second time here? That's how reverse shading works. Exactly. Then my range is somewhere between 2.8 and 3.2, because when you do reverse shading, your answer is where you haven't shaded. Does that make sense?
Yeah.
So it's actually something we do in math a little bit later. So indicators are actually fairly accurate. However, they are not precise. Let me say that again. Indicators are often fairly accurate. By that I mean they're very reliable. Indicators, you can't really screw up an indicator, because you guys know how yesterday with the pH meters, they weren't really calibrated. You don't have to worry about calibrating an indicator because it will work. It should. Does that make sense? The problem is they're not as precise. What do I mean by that? How many sig digs do you get? 1 sig dig. Hang on, 3.2, that has 2 digits. The first number, though, doesn't count. That makes sense? So in terms of precision, although indicators are very accurate and reliable, they're not very precise because you're only going to get 1 sig dig based on this. So I would prefer to, if I could, have the pH meter, because the pH meter might have said 2.99. Now I get 2 sig digs. The only problem with my pH meters is I don't think they're very reliable / accurate. Does that make sense? Okay, let's try another one. Phenolphthalein is colorless. So make another number line, 0 to 14. Maybe put a 7 in the middle so you have some perspective. Phenolphthalein being colorless, what does that tell you? Phenolphthalein is the 5th one from the bottom. It's from 8.2 to 10, but the colorless is on the 8.2 side. So we need to shade everything above 8.2. Otherwise it'd be pink. Does that make sense? Indigo carmine is blue. Indigo carmine is the very last one, second last one. And it's blue if it's less than 11.4. So way up here at 11.4, I know it's less than 11.4. Am I actually helping anything by shading this in? No, I mean, sure, I'll just re-shade it, but it doesn't actually add anything extra. So, last one, phenol red being red. Phenol red being red, phenol red is the 6th one from the bottom. It goes from 6.6 to 8.0, and if it's red, it's greater than 8. So I'm just going to put an 8 right here, and that means I have to shade the less than 8 side. So what's the range of my pH? Yeah, somewhere between 8 to 8.2 is my range. Again, fairly accurate. Indicators are quite reliable, but you only get 1 sig dig. So they're not actually useful for doing calculations with, because 1 sig dig isn't enough for that. Does that make sense? Okay, you guys try the last one then. It's not a particularly long topic, obviously. Like, this is it. Hopefully when you're done, don't look until you are, but hopefully you have something like my chart when you're finished here. Either that or I screwed up.
How did you get 4.8 for the last one? It turned orange. Doesn't that mean
That one was methyl red, correct?
Yeah.
So methyl red being orange is like, you know how it goes red to yellow? Orange must be in the middle of that. That makes sense, like how methyl red, orange is not a color listed for that. It goes red to yellow. So if it must be orange, it must be in between 4.8 and 6. Does that make sense? Oh, I come here. I just put a 7 on there because I just wanted to correct it. So like, really the last one's all you need. Methyl red being orange, there is no orange listed, right? So if it's orange, it must be in between 4.8 to 6. And that's, I mean, that actually was the most narrow down I was able to do. Yeah, because what I ended up getting is the 4.8 to 6 were the oranges. That actually is the most narrowed down I ever got, actually. Okay, so I think you must have done methyl red one wrong. Because methyl red is red to yellow, but I said it was orange. So if it's orange, it has to be between 4.8 and 6. So I would shade everything lower than 4.8, shade everything higher than 6. Yeah. So the shade less than the 4.8 and shade higher than 6. To be honest, the first two indicators we used didn't actually help narrow it down all that much. Really, that last indicator, that's what really narrowed it down. Anyone have any questions? Does that make sense? Pretty much. It's not the hardest topic in the world. It's actually kind of nice. We've covered most of the tricky topics up till now, just so you guys know. We have one more tomorrow, but it's also another short topic. So, why don't I just look at the slides I skipped in case there's anything I should talk about on those ones. Here's a picture that just has all of the different ranges that indicators can have. The more indicators you have, the more accurate you're going to be able to be because you can narrow down that range more and more. Does that make sense? So let me describe to you again your lab on Thursday. I'm going to give you a solution. I will know the pH. You guys won't. And I'm going to ask you to find the pH. So you're going to take the solution and put it into like 10 different test tubes. You only need just a little bit in each test tube. And then you're going to add 10 different indicators, one to each test tube. And what you'll do is the first one will say, well, it's less than this. The next one will say it's more than this, and then less and more. And by the time you're done shading, hopefully you'll only have like a little sliver left, and that will be the range for your pH. Then you're going to come ask me what the pH actually was, and hopefully what I tell you jives with what you just got. Does that make sense? If that works, then you're successful. If I tell you the pH is 9.2, and you think the range was from 1.1 to 1.3, then no, the lab was not successful. It's actually a very easy lab. It's just very time consuming because you have to like drop. You have to like organize it all. So. Oh, one more thought here. I did skip a slide that probably is worth talking about. Sorry, don't put it away just yet. Indicators are useful for finding the pH of a solution. That's what we're going to do in this lab. However, indicators actually have another use, but it's kind of something we're not going to talk about till later in the course. This is going to be a question that comes up on your lab. There is another use for them. They're used at what are called endpoints in neutralization reactions, and we're going to talk about this in our third unit. So just like put a star next to the slide. When I ask you what the two uses for indicators are, just know that there is another use for them that we're not ready to talk about yet. So much more context. The main use for right now is find a pH. So put a star next to this. Remember that like in a month when I want to talk about this slide, remember that we talked about indicators before. Okay, I think I'm done. Okay, here are some questions if you'd like to have some textbook questions. To be honest though, you guys should probably work on either your lab that we did yesterday. I'll print off the lab we're going to do Thursday so you can start on that. Your assignment, studying for tests. Tomorrow's our last set of notes, by the way. Then we're done the unit.
So, is it a work day on Thursday?
No. So tomorrow,
Thursday's the last.
yeah, tomorrow's our last set of notes. It'll probably take us about 45 minutes, maybe less than that. Thursday's a work day. Then we have a long weekend. Oh, sorry, Thursday's a lab, and then long
And
weekend
then
test, workday test. Yeah.
And then for math, it's test on Thursday,
Yeah.
grade, workday test.
Yeah. I'm trying to stagger them on the off days, because otherwise you have to like write it. Well, you're gonna write a test every day, but I think that's better than writing 2 tests in a day.
Yeah.
It sucks because both our units finish at like the exact same time. Okay. Let me know how I can help. You guys have about 25 minutes.
I missed the lab.
Okay. So for